Okay, so hello everyone. Welcome to the live problem solving session for week 8 of the course Computational Competitive Algebra. So let's summarize the topics of week 8 and then we will start solving some problems. So the keywords. So in week 8 we started with some properties of Artinian rings. So properties of Artinian rings. So there we have studied things like theorems like in Artinian ring the nil radical is same as the Jacobson radical, and in Artinian ring there are only finitely many maximal ideals, and also the nil radical is nilpotent. That means in Artinian ring if we take some power of the some large sufficiently large power of the nil radical, it will be zero. Also, a ring is Artinian if and only if it is Noetherian and it has Krull dimension 0. So there are some these theorems actually we have seen in the last week, and after that we have defined the composition series or Jordan-Holder series. So composition series, and then we have proved that Jordan-Holder theorem. So Jordan-Holder theorem. So which says that if a module has a finite composition series or it has a composition series, then every composition series has the same length. And using that, we have defined length of a module. And we have studied some properties of this, like a module has finite length if and only if the module is Artinian as well as it is Noetherian. And in case of a ring, we know if a ring is Artinian, then it is Noetherian. So a ring is Artinian if and only if it has finite length. So after that, we have defined graded rings and graded modules. So graded rings and modules. And in this setup, we have defined what do we call that Hilbert functions as the length of the homogeneous components of a graded module. So Hilbert functions, then we have proved that theorem that Hilbert functions will coincide with a polynomial with rational coefficients after a certain stage, and that is what known as Hilbert function, Hilbert polynomial. And using this, we have defined for a local ring, we pass to the its associated graded ring and defined Hilbert Samuel function to study Noetherian local rings. And the corresponding polynomial is known as Hilbert Samuel polynomial. So yes, of course, for these things we have defined the associated graded ring, these objects, graded objects, and also the associated graded modules. associated graded module. And using this terminology, Hilbert-Samuel polynomial, we want to basically prove the Krull dimension theorem. So for which we have defined like delta m, which is the minimal number of elements to generate an m primary ideal. And also we have defined, so this is basically minimum of mu of I such that I is an m primary ideal. And also we have defined S of m, the length of system of parameters. So yes, we have defined system of parameters, then we have defined S of m. So we have defined, and after that we have defined S of m, this invariant. And then we told that we will prove that delta m is same as S of m, and this is also same as the Krull dimension of m for a Noetherian local ring. So this is our one goal. And for that we need some preparatory lemmas and theorems. So for that we have defined what do we call I-stable filtrations, and the celebrated Artin-Ries lemma. So yes, we end up with these things. So these are the topics of week 8. Okay, now we can start solving some problems based on these topics. So let's start solving some problems. Okay, let's start with some easier ones. So the first problem is, so find the Jacobson radical of the rings. So the first one is okay, of the ring R, where you can take R as uh, the polynomial ring Zx and go modulo it by 9, ideal generated by 9 comma x. And the second one you can take R as let's say Z mod 140Z. Okay, let's do this only for these two rings. Okay, so first let's recall what is Jacobson radical. So if you take a ring R, then the Jacobson radical of R is basically you take the intersection of all maximal ideals of R. So that is the definition. So it is intersection of all maximal ideals of R. And also this is same as all those elements of R such that 1 minus xy is unit for all y belongs to R. So this is something we have seen in the lectures. So this is one characterization of the Jacobson radical. So but here we will use this first one, the definition, to calculate the Jacobson radicals. So for the first one, so to calculate the Jacobson radical, we need to find this intersection. So we need to find the maximal ideals. So let's find the maximal ideals of these rings. So here R is uh, okay. So here R is this quotient ring zx modulo ideal generated by 9 comma x. So what are the maximal ideal of this ring? So as this is a quotient ring, so let M be a maximal ideal of R, right? Then we know that by the correspondence theorem, the maximal ideals of this quotient ring are in 1-1 correspondence with maximal ideals of Zx, which contains the ideal 9 comma x. Okay, then okay, let me write in that way. So let M be a maximal ideal of Zx such that M contains 9 comma x. So that will imply x and 9 both are elements of M. So 9 is in M. So but 9 is equals to 3 square is in M. So that will imply 3 is in M, because maximal ideal implies prime ideal. So that will imply 3 comma x is subset of M. But that will imply M is equals to 3 comma x, because 3 comma x is itself a maximal ideal. It is maximal ideal of Zx. So there is only one maximal ideal of Zx which contains this ideal generated by 9 comma x. So what is the maximal spectrum of R? So this is basically ideal generated by 3 comma x modulo by ideal generated by 9 comma x. So there is only one maximal ideal, and that will imply that Jacobson radical is the intersection of only one ideal. So it is this ideal itself. It is ideal generated by 3 comma x modulo ideal generated by 9 comma x. So this is the first one. So for this, Jacobson radical is ideal generated by 3 comma x modulo ideal generated by 9 comma x. So similarly, let's do the second one. So here our R is z modulo 140z. So what are the maximal ideals of R? So let M be a maximal ideal of R, maximal ideal of Z, such that M contains 140z. So now, so what are the maximal ideals which contains 140z? So 140z, okay. So 140, if you write the prime factorization, then it is basically 2 square times 7 times 5. So that will imply the only prime ideal is, so M can be 2z or 5z or 7z. So all these three are prime ideals as well as maximal ideals in Z, because Z is a PID. So we have only three choices. So from that we can conclude the maximal spectrum of R. We have three maximal ideals, which is 2z modulo 140z, 5z modulo 140z, and 7z modulo 140z. So we have got all the maximal ideals of R. Now to find the Jacobson radical, we need to take intersection of these maximal ideals. So the Jacobson radical of R is basically 2z mod 140z intersection 5z mod 140z, and again take intersection it with 7z mod 140z. So this is basically 2z intersection 5z intersection 7z modulo by 140z. Now how to calculate this intersection? It is basically the LCM. So LCM of 2, 5 and 7, which is 70. So it is 70z modulo 140z. So this is the Jacobson radical for z mod 140z. So for this one, it is ideal generated by 3 comma x modulo ideal generated by 9 comma x, and for this one it is 70z modulo 140z. So this is the solution of second one. Okay, so now we can do the next problem. So the second one is, so I already mentioned that for a ring R, the Jacobson radical is basically intersection of all maximal ideals. And also there is something called the nil radical, which is intersection of all prime ideals. Right? So, and maximal ideals are prime ideals. So since this maximal spectrum is subset of the spectrum, because maximal implies prime, so this nil radical is always subset of this Jacobson radical. Right? So this is something we have seen from the lectures. So the next problem is about, so we have to give an example where this equality need not hold. So so we have already seen that in a Artinian ring, these two ideals has to be same. In a Artinian ring, nil radical is always equal to its Jacobson radical, but it need not be equal always. So give an example of a ring, let's say R, such that the nil radical is a proper subset of the Jacobson radical of R. So to give such example, we need to take non-Artinian ring, because in an Artinian ring, these things are equal. So recall, if R is Artinian, then this nil radical is equals to Jacobson radical. So we need to take some ring R which is not Artinian. Okay. So what kind of ring then we can take? So let R be the power series ring in one variable over a field K. So where K is a field. So this is the ring of all formal power series uh, over K in one variable X. So then note that means I think you can recall it. Then this R is a uh, principal ideal domain. R is a principal, okay, local principal ideal domain is a local PID with maximal ideal, the ideal generated by X, and every other ideal is power of this maximal ideal. So now it has only one maximal ideal and it's a PID, means it's an integral domain. So in an integral domain, we cannot have any non-zero nilpotent element. So since R is an integral domain, the nil radical of R, okay, let me write the nil radical of R is basically 0. So we have only one nilpotent element, which is the 0. But if we calculate the Jacobson radical, it is intersection of all maximal ideals. But we have only one maximal ideal, so it has to be ideal generated by X, and which is this is non-zero. So hence the nil radical is proper subset of Jacobson radical in this case. So basically, so you can generalize this example. So let me put that as remark. So instead of kx, we can take any local domain, any local integral domain. So why we can take? Because if we take any local integral domain, since it's a domain, so its nil radical is 0, but it is a local. So local integral domain which is not field, uh, which is not field. So in that case, we have only one maximal ideal which is non-zero. So that has to be the Jacobson radical, which is non-zero, but the nil radical is 0. So from this we can conclude a local integral domain which is not a field, uh, that cannot be a Artinian ring. So this is the first one. So we can conclude that a local integral domain which is not a field cannot be Artinian. So something more general actually is true. So I will write it here. So this is an Artinian integral domain. An Artinian integral domain is always a field. So here we don't need local, so we just need Artinian integral domain is field. So this is something not difficult to prove. So one may try to prove this, but if you are not able to prove, you may refer to standard texts. But this is something you should know. So this is just for your information. Okay, so now I think we can move on to the next problem. Okay, question number 3. So this is a true false type question. So let R be a ring such that the Krull dimension of R is 0. So dimension of R is 0. So then R is an Artinian ring. So this is true or false. So R is such that dimension of R is 0. So does that imply R is Artinian or not? So recall from the lectures that if R is Artinian, then we know that dimension of R is 0, because every prime ideal is maximal. So it has to its dimension has to be 0. So it is asking about the converse. So recall from the lectures that the converse is true if and only if R is Noetherian and dimension 0. So this statement is not true if we find a ring which has dimension 0 but it is not Noetherian. So this answer is actually false, but we need to give some counter example. So okay, so first I will write that recall a ring R is Artinian if and only if R is Noetherian and dimension R is 0. So this statement is not true. So this we can say directly from this result, but let's give some counter example for better understanding. So we need to find some non-Noetherian ring which has dimension 0. So one non-Noetherian ring which is very standard example we know is you take a field and you take the polynomial ring in infinitely many variables. Right? This is a non-Noetherian ring that we know from the lectures, because this ideal generated by all the variables, it is not finitely generated, so it cannot be Noetherian. But this ring has positive dimension, right? Because x1 is properly contained in x1 comma x2 and so on, so it has infinite Krull dimension. So from this what we will do is, so we will go modulo by the ideal generated by x1, x2 square, x3q, and so on. So let's take R to be this ring, right? Then uh, R is non-Noetherian, again because of the same reason, but you can work out the details. Because the ideal x1, x2 generated by all the variables modulo by x1, x2 square, x3q, and so on, this is not finitely generated. Okay, so this you can work out. But what is the dimension of R? So as this is non-Noetherian, this is not Artinian, right? Hence, uh, R is not Artinian, because Artinian rings are always Noetherian. So uh, because Artinian implies Noetherian. But what is dimension of R? Okay, now what is dimension of R? So recall, dimension of R is basically if you take chain of prime ideals. So this is basically the maximum possible length of chain of prime ideals in R. So let's find the prime ideals of this ring. So again we need to find the prime ideals of this quotient ring. So we will use the correspondence theorem. So prime ideals of this ring, basically the prime ideals of this polynomial ring which contains the this ideal. So let P be a prime ideal. Let P be a prime ideal of the polynomial ring in infinitely many variables such that this P contains ideal generated by x1, x2 square, x3q, and so on. Right? Now this will imply, if you take the variable xi, its ith power should be in P, and this is for all I greater or equals to 1. But P is a prime ideal. So that will imply xi itself belongs to P for all I bigger or equals to 1. So this is because P is prime. Now what does this means? So that will imply all the variables is in P. So x1, x2, x3 dot dot all the variables. If you take the ideal generated by all the variables, this has to be subset of P. But this ideal is maximum because if you go modulo by this, you will get K. So this will imply P has to be equals to ideal generated by x1, x2, and dot dot so on. So this is because x1, x2, dot dot so on is a maximal ideal of k x1, x2 up to, so polynomial ring over infinitely many variables. Now what does it say? So this means there exists only one prime ideal of this ring R. So spectrum of R is basically the ideal generated by x1, x2, dot dot so on, go modulo by x1, x2 square, x3q, and so on. So since there is only one prime ideal, so we cannot have any chain. So dimension has to be 0. So dimension of R is clearly 0. So this gives the counter example which we are looking for. So this is an non-Artinian ring which has dimension 0. Okay. So now we can move on to the next problem. Okay, so let's find the dimension of some rings. So this is problem number 4. So find the full dimension of the following rings. So the first one is Z mod, let's say 12Z direct sum with Z, or we can take direct product because it is finite. Second one is Z mod 12Z direct sum with Q, and third one is Z direct sum with Q. So how to find true dimension of this type of rings? So basically here we want to find uh, true dimension of a ring of the form, let's say R. Okay, we should not take direct sum, let's say it's Cartesian product because we are taking rings. So we want to find true dimension of a ring of the form R cross R prime, right? So we need to look at the chain of prime ideals of R cross R prime. So how the prime ideals of R cross R prime looks like. So what are the prime ideals of R cross R prime? So first observe that uh, every ideal of this ring R cross R prime has the form I cross I prime, where I is an ideal of R and I prime is an ideal of R prime. So this is something very easy. So you can do it by yourself. So I will just put it as exercise, or maybe you can go back to your ring theory course and review the things there. So if you take this ring R cross R prime, and if you take an arbitrary ideal, then arbitrary ideal has to be in this form I cross I prime. Now how prime ideals looks like? So second one, if P cross P prime is a prime ideal of R cross R prime, then uh, so if we are taking a prime ideal of this ring, so then what can we say? So then the corresponding quotient R cross R prime mod P cross P prime must be an integral domain. So this quotient is an integral domain. But how this quotient looks like? But R cross R prime modulo P cross P prime is basically same as R mod P cross R prime mod P prime. So this is a direct product of two rings. So when this is an integral domain, so R mod P cross R prime mod P prime is an integral domain if and only if one of this is integral domain and other is zero. One of R mod P comma R prime mod P prime is a domain and the other one is zero. So that means so that will imply uh, one of P comma P prime is a prime ideal and the other one has to be the whole ring and the other one is the whole ring R or R prime. So uh, so what is the conclusion? So how the structure, what is the structure of the prime ideals? So every prime ideal of R cross R prime must have one of the following two structures. So we have only two possibilities. So first one is it is either a prime ideal of R direct product with R prime, where P is a prime ideal of R, or it is the whole ring R direct product with P prime, where P prime is a prime ideal of R prime. So these are the only prime ideals of this product ring. So if we take R and take a chain of prime ideals, let's say P1 P0 up to Pn, then this will correspond to a prime ideal like P0 cross R, proper subset of P1 cross R, and proper subset of Pn cross R prime. So here we have R prime. So for every chain R, we have a chain of primes in R cross R prime. Similarly for the other one. Similarly, if you are in R prime, like P0 prime proper subset of P1 prime, proper subset dot dot so on, then this will correspond to a chain of prime ideal in R cross R prime. So thus, clearly, the Krull dimension of R cross R prime is basically same as maximum of dimension of R, comma, dimension of R prime. So this is something I have explained, but I have not written the details. So that you can write on your own language. So just fill out the details. So fill out the details. So this is the thing we are looking for. Now let's use this thing to prove to do the problem, to find the dimension of these following rings. So let's do the first one. So here R cross R prime is basically Z mod 12Z cross Z. So what is dimension of R here? Means dimension of Z mod 12Z. So both of these dimensions are 1. So dimension of Z is 1 because it's a principal ideal domain which is not a field. But for this one also Z mod 12Z, it is also principal ideal ring but not a domain. So it has also dimension 1. So dimension of Z mod 12Z cross Z is equals to 1. So this is the first one. Now what about the second one? So what about dimension of Z mod 12Z cross uh, Q, the ring of rational numbers. So again it is the maximum. So maximum of 1 and dimension of Q is basically 0 because Q is a field. So it is also 1. So because dimension of Q is 0. Now what about the third one? It is dimension of Z cross Q. So again it is maximum of dimension of Z comma dimension of Q. So it is maximum of 1 comma 0. So it has to be 1. So one thing I want to mention that, so this I have done only for 2 rings. So you can take infinitely many rings also. So in that case you might take at supremo. So in that case same idea will follow. Okay. Okay, now let's do some problems on Hilbert functions. So this is problem number 5. Yeah, so problem number 5. So find the Hilbert polynomials of the following rings. Okay, so the first one, okay, let's take some easier ones. So first one is, you take the polynomial ring kxy, go modulo by the ideal generated by x times y. Second one is, you take, again you take the polynomial ring kxy, and go modulo y, the ideal generated by x square and y cube. Okay, so we need to find the Hilbert polynomials of these following rings. So let's recall what is Hilbert polynomial. So suppose you are given a n graded ring, a Noetherian graded ring. So our graded rings are always n graded, where R naught is Artinian ring. Then each Rn is finitely generated R naught module. So that will imply length of Rn over R naught is finite for all n greater equals to 0. So this function h r of n defined as length of this is the Hilbert function of R, and there exists a polynomial, let's say px belongs to qx, such that h, okay, so we denote this polynomial as pr of x, such that phr of n is same as pr of n for all sufficiently large n, and we call prx the Hilbert polynomial of R. So here we need to find this Hilbert polynomial in these two cases. So let's do the first one. So here R is kxy modulo generated by xy with the standard grading, means degree of x is 1 and degree of y is 1 and degree of k is 0. So if we write the grading, it is basically k direct sum. So remember that xy, if we take product in this quotient, that will be 0. Product of xy is 0. So 1 degree terms. So in kxy, what are the 1 degree terms? It is kx, ky. So they will survive. So it is just kx direct sum ky 1 degree monomials. Now what are the 2 degree monomials? 2 degrees are kx square direct sum k, okay, we need to take bar because we are in quotient. So kx bar square, but if we take kx bar y bar, this thing is 0 in the quotient, so we don't need to write it. So it is just ky bar square. And what is degree 3 term? Again kx bar q direct sum ky bar q and kx bar y bar square, but again x times y will be 0, so it will be 0. And again kx square y bar, so this is also be 0, so we have only two terms. So again two terms of degree 3. So similarly we will get only two terms. So this is this one degree 0, this part degree 1, this part degree 2, this part degree 3. So now we need to find the Hilbert function first. So h r of n is basically lambda k of Rn, length of the nth component. But over k, length of module over a field. This is same as vector space dimension. So dimension of Rn over k. So zeroth component it is k. So for zeroth component dimension will be 1 when n is 0. For n equals to 1 it is kx direct sum ky. Kx is isomorphic to k. Similarly ky. So it is dimension 2 for n equals to 1. And similarly for n equals to 2 and 3. So for n greater equals to 1 the dimension will be 2. So this Hilbert function is constant function from n greater equals to 1. So clearly the Hilbert polynomial, it is just the constant polynomial. And it is coinciding from the stage 1, n equals to 1. So this is the first one. Now what about the second one? So in the second one, our ring R is basically kxy modulo by the ideal x square y cube. So we need to see the graded components. So as usual, the zeroth component will be k, it will survive. The 1 degree components will also survive. Now what about the second degree components? So x square is 0, so x square will not be there. So k x bar y bar will be there and k y bar square will be there. Now what about the third degree component? So x square 0 means xq will also 0. So xq 0. So what are the possibilities for degree 3 polynomials? So we need to find degree 3 monomials first. So let's write down, it is xq, xy square, x square y and yq. Now this one is 0, x square y this is 0, yq is 0. But xy square is non-zero. So there will be only one term, kxy square. So this is for degree 3. Now what about degree 4? Is there any degree 4 term? So what are the all degree 4 terms? So it is x power 4, x y cube, x square y square, x q y and y power 4. But x square 0, x y q 0. So x square 0, y q 0. So x power 4 is also 0. Since y q 0, so this is also 0. X square 0, so this is 0. Again x q is 0 and y power 4 is also 0. So from degree 4, all the terms are 0. So we have only terms up to degree 3. All other terms will be 0. So this one is 0 degree. This one is degree 1. This part has degree 2. This part has degree 3. And Rn, nth degree term is 0 for all n greater equals to 4. So let's write down the Hilbert function. So h r of n, length of the zeroth component which is k of Rn. This is same as vector space dimension of Rn. So what about the dimension? So zeroth component is k, so dimension is 1 for n equals to 0. For n equals to 1, kx direct sum ky. Kx is isomorphic to k, ky is isomorphic to k. So this is k square. So dimension is 2 for n equals to 2, sorry, n equals to 1. But degree 2 also same. Kxy is isomorphic to k, this is isomorphic to k, and you are taking direct sum. So this is just k square. So this is for n equals to 1 and 2. But for n equals to 3, it is kxy square. This is same as isomorphic to k. So dimension is again 1 for n equals to 3. And for n greater equals to 4, the module is 0. So it is 0. So from n equals to 4, we are getting 0, constant. So Hilbert polynomial is also constant. So it is easy to guess. So Prx is 0 polynomial, and it is coinciding with the Hilbert function from 4. So this is the Hilbert function, sorry, this one, and this one is the Hilbert polynomial. Okay, so this was problem number 5. Okay, now let's do one problem on system of parameters. So problem number 6. So it is true false. So let R be the ring. You take the formal power series ring in two variables and go modulo by x minus y square, where k is a field. Okay, so then the element x bar belongs to R is a system of parameter of R. So this is true or false. So we need to check this element is a system of parameter of R or not. So let's recall what is the system of parameter. Uh, yeah. So let R comma M be a Noetherian local ring. Then a set of elements, let's say, okay, I will write A1 up to AR belongs to the maximal ideal, is said to be a system of parameter of R if you go modulo by this ideal generated by A1 up to AR, then this quotient ring, then length of this quotient ring over R is finite. If length of this quotient ring is finite, then we say this element A1 up to AR is a system of parameters. So we need to check. So we need to check length of R mod X bar is finite or not. So what is R mod X bar? So this is the power series ring modulo x minus y square, again modulo by x comma x minus y square. Right? Now use the third isomorphism theorem. So this is same as, so I will write here only. So this is same as power series ring modulo ideal generated by x. So we are going modulo by one variable. So this is same as power series ring in y. Sorry, I am doing some mistake here. Sorry, this is, so if we go modulo by x, so we will have only ky, right? So this is same as, okay, so I have written wrongly here. So this is this ideal modulo ideal generated by x minus y square. So this is same as kxy modulo x comma x minus y square. So this is by third isomorphism theorem. So now we need to find this quotient. So if we go modulo by x, we will have only y. So if we x equals to 0, then x minus y square bar, this is become y bar square. So this is same as, sorry, ky modulo ideal generated by y square. So what is length of this module over R? Okay, so we need to find length of ky modulo y square. So we know, okay, I will write here. We know length of a module is finite if and only if M is Artinian as well as Noetherian. Right? So we need to check it is finite or not. So we need to check it is Artinian as well as Noetherian or not. So since ky is a PID, so that will imply ky is Noetherian, and it is, this one is quotient of a Noetherian ring, so this is also Noetherian. But it is Noetherian. Now what is dimension? And dimension of this is 0, because dimension of ky is basically dimension, it has one variable, so same as polynomial ring, so it is a PID, so its PID is dimension 1, and y square is a non-zero divisor on ky. So this one is because ky is a PID. So it is PID, so it has dimension 1, and you are going modulo by a non-zero divisor or a regular element. So dimension will reduce by 1, so it is 0. So it is Noetherian and dimension 0, so that will imply ky modulo y square is Artinian as well. So it is Noetherian as well as Artinian, so it has finite length. So in this case, length over itself we are finding, but length over R also same. So its length is finite. So definitely X is a system parameter for R. X bar belongs to R is a system of parameter. System of parameter of R. So this is true. Okay, I should write it in black. So it is true. Okay, so let's move on. So this is problem number 7. So this is from the practice problem set. So recall that if K is algebraically closed field, and if you take the polynomial ring kx1 up to xn and an ideal of R, then uh, then the zero set of I, it is finite if and only if R mod I has finitely many maximal ideals. So this is something we have seen in the lectures. Okay, but one thing it is important that here this K has to be algebraically closed. Otherwise, this statement need not be true. So we need to give an example that this statement is not true when the field is not algebraically closed. So let's write down. So give an example uh, of an ideal I in a ring R equals to K x1 up to xn, where this K is a field such that this Z of I, the zero set of I, is finite, but the quotient R mod I has infinitely many maximal ideals. So R mod I has infinitely many maximal ideals. Okay, so we need to give such example. So because of this result, we need to take K where K is not algebraically closed, right? So we need to take K which is not algebraically closed, right? So let R to be the polynomial ring over Q in two variables. So Q is definitely not algebraically closed, that we all know, and let I to be the ideal generated by x square plus 1. Then what is zero set of I? So this is the set of all polynomials. So this is all x comma y belongs to Q2 such that uh, every polynomial of I vanishes at this. So only x square plus 1 is there such that x square plus 1 is 0. But there is no such real number, right? So this has to be an empty set. So that will imply, because this polynomial has no solution is in Q. In fact, it has no solution in R. So cardinality of zero set of I is 0. It is finite. But if you see R mod I, so this is basically Q of x comma y modulo by x square plus 1. Okay, let's take R itself instead of Q. So the things become more easier. The real number. For Q also it is true, but let's do the thing in an easier way. So what about this quotient? So recall that if you take Rx and if you go modulo by x square plus 1, this is isomorphic to C. So this is something going on. So here it will be isomorphic to C of y. So R mod I is isomorphic to C of y and C is algebraically closed. So maximal spectrum of R mod I is uh, is in 1-1 correspondence with maximal spectrum of C of y, but this is in 1-1 correspondence with C. This is by Hilbert-Nullstellenscher. So there are infinitely many maximal ideals in this quotient ring. So R mod I has infinitely many maximal ideals. Okay, so this is the required example which we are looking. Okay. Uh, okay, let's do the next one. This is problem number 8. So this is also from the practice problem set. So compute the associated graded rings, associated graded rings uh, with respect to the maximal ideal in the following cases. So the first one is, the ring is, you take Z and localized it at a prime ideal. So where P is a prime number and your maximal ideal, because it's a local ring, it has only one maximal ideal, so it is just PZP. And the second one is, again we need to take a local ring. So let's take the formal power series ring in two variables and the maximal ideal generated by x comma y. So we need to find the associated graded ring. So let's see the definition of associated graded ring. So recall uh, the associated graded ring of R with respect to the ideal M is basically uh, you take direct sum of m power n modulo m power n plus 1. This is from n greater equals to 0. So this is basically R mod m direct sum, m mod m square direct sum, m square mod mq direct sum, so on. So we need to find explicitly this graded ring in these following two cases. So what is the first one? So let's write it here. So here R is ZP and M is P mod ZP. So here the associated graded ring is, so first one is R mod M. So it is Z localized at P modulo by its maximal ideal. Then take direct sum P square by ZP modulo by, sorry, P mod ZP. The maximal ideal modulo by its power, which is same as P square extended to ZP, same as sorry, the next one is P square extended to ZP modulo PQZP, and so on. So we need to find each of these factors. So I will just write down it. The rest part you can do. Observe that if you take P power n and extend it to ZP and go modulo by P power n plus 1 and extend it to ZP, this is same as uh, ZP, Z localized at P modulo by its maximal ideal, and this is true for all n greater equals to 0. So this part I am leaving up to you. Okay, now what about this part? So we know localization uh, commutes with taking quotients. So if you take quotient first and if you localized it, then these two are same. So localization commutes with taking quotients. But what is this? So Z mod Pz, it is a field. So if you have a field and if you are localizing it, so you will not get anything new, because localizing means adding more units. And in a field, every non-zero element is unit. So we cannot add more units. So it has to be isomorphic with Z mod Pz. Because Z mod Pz is a field. So now let's see this one. So our associated graded ring is basically Z mod Pz direct sum Z mod Pz itself infinitely many times. So this is direct sum of Z mod Pz where n is greater or equals to 0. So it is a free module over Z mod Pz. So this is same as you take Z mod Pz, the polynomial ring in one variable over Z mod Pz. So this is just an observation because it's a free module of Z mod Pz. It is also free module of infinite rank of rank uh, n over Z mod Pz. So these two are same. Okay, so we have done the first one. Now let's do the second one. So B. So again, let's write it down. So first term is again R mod M. So it is kxy modulo x by y. Sorry, kxy modulo the maximal ideal x comma y. Direct sum the maximal ideal modulo by its square. Direct sum square of the maximal ideal by the cube of the maximal ideal, and so on. Okay, now this is by the definition. So now we need to find each of these factors. So first one is very easy. So we are going modulo by the variables. So it is just k. Now what about this second one? xy modulo xy square. So xy means generated by degree 1 terms. Xy square means generated by degree 2 terms. So we are killing all terms which has degree 2. Degree 2 onwards, all terms will be 0. So only degree 1 terms will be survived. So this is kx modulo ky, because only degree 1 terms will survive. Similarly, here degree 2 terms are there and going modulo by terms of degree 3 onwards. So degree 2 terms will only survive. So this is kx square direct sum kxy direct sum ky square and so on. Now what is this? So what can we say about this one? So this one is degree 0, this one has degree 1, this one has degree 2, and so on. So this is simply looks like the polynomial ring over k in the variables x and y, right? Because these are giving degree 1 monomials, these are degree 2 monomials, next one will give degree 3 monomials, and so on. And we are taking direct sum of them. So clubbing all together, we will get the polynomial ring over k in two variables x and y. So this is the associated graded ring. So we have done all these two problems. Okay, so more or less we have covered all the parts. So it's better to stop now. Yeah, so more or less we have covered all the parts except the art in Islam so on, but that's okay because art in Islam is used only for the uh, equality of these three numbers. That's okay. Okay, so let's stop here today. Again, we will meet in the next week.